Hello and welcome to this very brief presentation that introduces the calculation of bending moment diagrams associated with simply supported beams that have point loads only applied. I'm going to show you a brief example extracted from our workbook, and then I'll outline solutions to various questions, again from the workbook. So example 5, for the beam shown, we're asked to calculate the bending moments along the beam at various points, labelled A, this would be A, C, it's point C, D, point D, and B, shown here. The labelling is totally arbitrary. You can label the various points along the beam as you prefer. I'm using the A at the left-hand end because the reaction RA is stated at the left-hand end, and I'm using B for the right-hand end simply because the reaction RB is stated at the right-hand end. We're given the load and applied. We have 2 point loads, 4 kilonewtons, 1 metre in from the left-hand end, and 6 kilonewtons, 3 metres from the left-hand end. We have our distances to the point loads, and we have the overall length of the beam. This presentation does assume you've seen previous presentations related to calculating the various reactions, RA and RB here, but to speed up the process of the lecture, we're given in this case reaction RA is 5.6 kilonewtons at the left-hand end, and reaction RB is 4.4 kilonewtons at the right-hand end. What we're going to do is calculate the bending moments at points A, B, C, D along the length of the beam, and then we're going to actually draw a bending moment diagram. So example 5. Just note for reference, all the forces we'll be considering in this presentation are in kilonewtons. So the first thing we're going to do is calculate the bending moments. So to do this, we consider bending moments to the left of or the right of the various points across the length of the beam. Bending moments calculated to the left of a point or to the right of a point must be the same for the beam's equilibrium. Newton's third law effectively in application there. So to be consistent, I'm going to initially take bending moments to the left-hand side of each of the points as we move across the beam, but in later questions you'll see I'll also consider bending moments to the right, because sometimes it's easier to calculate bending moments to the right of a point than to the left. Let's consider bending moments to the left of the points A, C, D, and B on our beam. Remember from our previous work, a moment is defined as the force multiplied by its perpendicular distance from the point we're considering. And for a recap from our previous presentation, when we were considering moments, we used the analogy of a spanner. And for the diagram shown here, we're calculating the turning moment about point B, which is where the nut is located. And to calculate the turning moment, also termed the torque in this particular instance, the formula is simply moment about B, the force applied here at the end of the spanner, denoted as F, multiplied by the perpendicular distance shown here that the force is applied away from the turning point, or the nut in this case, point B. So that's labelled as lowercase d here. So force multiplied by perpendicular distance from the point about which we're considering the moment is how we calculate the moment. Note for the illustration shown here, the moment is in the anti-clockwise sense. MB is anti-clockwise. As a recap slide, if we now consider the turning moment about point A, labelled here, again the moment about the nut is calculated from the formula MA is equal to the force applied here at the end of the spanner, labelled F, multiplied by again the perpendicular distance the force is applied from the point of rotation, D. So the moment at A is F multiplied by D again. This time the sense of the moment is clockwise about point A. So that shows you the definition of a moment, but in the context of applying force at the end of a spanner. Hopefully that aids your realization of the concept of a moment. We're obviously not considering moments about nuts, or we're considering moments about points on the beam, but those points can be considered the nut for analysis purposes. So initially I'm considering the point at A. If I look to the left of A, what do I see? I see absolutely nothing. There's no forces to the left of A. So we often say that the moment at A is zero by inspection. Simply looking for the bending moment to the left of A, we can't see anything, so bending moment A must be zero. If we now consider point C on our beam and we look to the left, we now see the 5.6 kilonewton force, the reaction force here, multiplied by the distance of 1 meter. Remember, a moment is a force times its perpendicular distance about the point we're considering. So considering RA from point C, that's where we have the 1 meter distance. If it helps, here again is the spanner analogy, considering bending moments or taking moments to the left hand side of point C. Point C on our beam. And for the spanner analogy, that's where the nut would be positioned. So to calculate the bending moment to the left of point C, this would be the spanner position. And the force applied at the end of the spanner is the reaction RA. So RA multiplied by the perpendicular distance from C, labelled as 1 meter here, would calculate the bending moment at point C. Notice the 4 kilonewton force does not generate a bending moment at point C because the line of action of the 4 kilonewton force passes directly through the nuts. So by definition, the 4 kilonewton force cannot generate a moment about C. So the bending moment to the left of C, MC, is 5.6 kilonewtons multiplied by the 1 meter. That's a moment of 5.6 kilonewton meters. Notice it's a positive bending moment because it has this effect on the beam. It's trying to what's called sag the beam. Think of the force 5.6 kilonewtons multiplied by 1 meter is trying to do this to the beam. It's trying to put it into this shape, this sagging shape on the beam. Just note for your reference these two types of beam shape shown here. Here's an illustration of a hogging beam and of a sagging beam. And it's a sagging beam that denotes positive bending moment. Let's next consider bending moments to the left of point D of our beam. So MD, what do I see when I look to the left of this point here? I see the 5.6 kilonewton reaction at the end, but this time it is 3 meters away from point D on the beam. So the 5.6 kilonewtons is multiplied by the 3 meter length down here. But also looking to the left of point D, I now see the 4 kilonewton force, this point load, which is 2 meters away from point D. And that's actually a negative bending moment now, because it's actually trying to what's called hog the beam. In other words, the 4 kilonewton force times 2 meters is trying to do this to the beam, the opposite sense to our positive bending moment. Again, here's a picture of our hogging beam. In our calculation, we minus the 4 kilonewton force multiplied by the 2 meters. Evaluating the bending moment at point D on the beam, 3 meters in from the left-hand end, is 8.8 kilonewton meters. Again, if it helps you understand, here's the spanner analogy, taking moments to the left-hand side, point D. So point D is where the nut would be located in the analogy, and here's the orientation of the spanner. And now moments are generated by RA multiplied by 3 meters. Here's our 3 meters. And also the 4 kilonewton force multiplied by the 2 meters from D. And finally, if we consider now point B on our beam, that's the right hand end. If we look to the right of point B, there are no forces applied to the right of point B, so by definition no moments applied. So the bending moment at B must be 0. Just to show that if we consider bending moments to the left of point B, we will also get 0. Here's my calculation. So now we have the 5.6 force, RA, but this time it's multiplied by 5 meters because we're 5 meters away from point B, so multiplied by 5. We subtract the 4 kilonewton force shown here, which is now 4 meters away from point B. This distance across here is 2 meters. So it's 4 kilonewtons multiplied by 4 meters here. And of course I now, looking to the left of B, also see the 6 kilonewton force, which is 2 meters away. So again, that induces a negative bending moment, so we subtract the 6 times 2. When you evaluate that, it does become 0, which of course we know by inspection to the right of B, moments must be equal to 0. And again, for your reference, here's the spanner analogy when we're now taking moments to the left-hand side of point B. So here's point B, where the nut would be located. This is the orientation of the spanner now. So what you see there is the basic process involved with calculating bending moments applied to horizontal simply supported beams when we're only considering point loads applied. Example 5, solution continued here. All we need to do now is actually construct the bending moment diagram. So step 2, as I've labelled it here, we're going to draw the bending moment diagram for our beam. And all we simply do is note the bending moments we calculated here, and we simply plot them on our diagram. The bending moment A was 0, bending moment at C was 5.6 kilonewton meters, bending moment at D 8.8 kilonewton meters, and of course the bending moment at B was 0. All we do now to construct the bending moment diagram is join these points with linear lines. They're usually cross-hatched for clarity, and of course we should always state the unit that's being used here, it's kilonewton meters, and state the positive bending moment notation. So that's the bending moment diagram for a simply supported beam with 2-point loads. I'm now going to extract some questions from our workbook, and for each question we have to calculate the bending moments at various positions along the span of the beam, and then draw the associated bending moment diagram. Note for reference that with all the questions, the forces or the point loads applied to the beam are in kilonewtons. So for question 1C shown here, this is a 40 kilonewton applied load, this is an 80 kilonewton applied load. For question 2C, we have 3-point loads, 60 kilonewtons, 80 kilonewtons, and 100 kilonewtons. Within each of the questions, we are given the reactions, RA and RB, to save us time in the solution. The bending moments at the various positions along the lengths of the beam are shown in the brackets. Full work solutions are shown to question 1 and question 2. Here's question 3 and question 4. Again, the forces stated in kilonewtons. And again, full work solutions shown in the presentation for question 3 and question 4. And I'll leave you with question 5 at the end of the presentation to develop a solution at your own pace. The answers for the bending moments across the beam are shown in the bracket here. So here's question 1. We're given in the question for reference a reaction at A here and the reaction at B here for reference. Said before, all the forces we're going to apply to our beam will be in kilonewtons. Even if the unit is not stated, we will assume kilonewtons. The answers for the bending moment at A, C, D, and B are stated here in the bracket. I'd encourage you to start the presentation and attempt question 1C, but I'll show you the full work solution on the following slides. Here's question 1C, commencement of the solution. I'm going to let you review the solution at your own pace. We've calculated the bending moments along lengths of the beam. Just notice I considered bending moments to the left-hand side of the various points for MA, MC, and MD. I then considered bending moments to the right-hand side of the last 2 points here. MD, just did this as a check. You can see the bending moment is the same whether you consider bending moments to the left or the right of the point. And also MB. Question 1C, solution continued. And here's the sketch of the bending moment diagram. for question 1C. Again, we join the points on the bending moment diagram using linear lines. They may not look quite linear here, but they're supposed to be linear on my sketch. Again, add in the unit used for the bending moments and the positive notation used. Here's question 2C. I'm going to let you review this yourself. As always, we're going to be given the reaction at left hand end and right hand end. Again, the forces are in kilonewtons, so that's 60 kilonewtons, 80 kilonewtons, 100 kilonewtons stated here, and the answers are shown again in the bracket. I'd encourage you to attempt this question, but the full work solution is shown on the following slides. Question 2C, here's the solution. Again, I'll let you review this at your own pace. And question 2C, solution continued. Here's our bending moment diagram. Again, quite crudely sketched. We have these linear lines between each of the bending moments that's been calculated along the length of the beam. Question 3C, forces applied here. We've got 40 kilonewtons left hand end and 90 kilonewtons applied here. Answers shown in the bracket. Full work solution shown on the following slides. So question 3C, beginning of the solution, and I'll let you review the calculations at your own pace. Question 3C, solution continued. Here's the bending moment diagram for the beam. Notice this time we have a negative bending moment at point A and a positive bending moment at point C. Shown here, negative bending moment, positive bending moment. Hence the shape of the bending moment diagram. Question 4C, this time the forces applied. 120 kilonewtons, 80 kilonewtons, 100 kilonewtons at these positions. Bending moments shown in the bracket. Full solution on the following slides. Question 4C, commencement of the solution. Here are the bending moment calculations. Consider everything here from the left hand side of the various points along the beam. Question 4C, solution continued. Just calculated a few points to the right hand side here, just for reference really. Question 4C, solution continued. Here's the bending moment diagram. And finally question 5C, I'll leave this question for you to develop your own solution. We're given the reaction at RA and RB in the question. Forces again in kilonewtons, we have 40 kilonewtons applied here, 100 kilonewtons applied here and 80 kilonewtons here. And the bending moments are shown in the bracket. As I say, I'll leave you with this solution to attempt at your own pace. For your reference, there are further presentations related to calculating shear force and bending moments applied to simply supported beams, where we consider beams subjected to uniformly distributed loads, UDLs, usually denoted by symbol lowercase omega, having the SI unit of the Newton per meter, and usually depicted in this form. And we also consider combined loading applied to simply supported beams, where we have point loads, shown here, and a uniformly distributed load, shown here, applied concurrently. But as I say, that's just for your future reference. I hope this presentation has been of use to you, and thank you for viewing.